Hi everyone, continuing with our lecture series in cluster analysis. This is where we are going to continue with the first of the three methods in cluster analysis, that is the hierarchical cluster analysis. This is my data set, and I request you to please go and watch my earlier two video lectures so as to understand this better. So we are continuing to use the same data set, and so these are the variables. Okay, so we're trying to make clusters out of some marketing information, marketing data. And about the output, we were able to understand about the agglomeration schedule last time. Now today, I'm going to tell you that where do we actually understand that, okay, this is the optimal number of clusters I was looking for. Because see, objective of hierarchical cluster analysis is indeed this, that you really want to come up with an optimal number of clusters, okay, which is, so this is the particular number which you will then use when you have to directly tell SPSS that, okay, for example, in k-means and two-step clustering, we'll tell SPSS that I want 3 cluster solution or a 4 cluster solution. So where is it coming from? It's coming from hierarchical. So hierarchical is the first of 3 methods for this very reason. So this is a very, very important lecture. So for agglomeration schedule, my sincere request to you all is that do not find it very difficult. Just look at the stage column and the coefficient column. I'll repeat for you. Stage means the stage at which the cluster first appears. You know that we're going to, we're really, moving ahead from n is to 1. That is, individually, each person or each case in our data set starts as a cluster, and towards the end, that is the last stage, everyone becomes a part of one big cluster. So you would have gotten to understand that if on stage 99, everyone in your data set became a part of one cluster, can you say that stage 99 can alternatively be looked at a one cluster solution? You're absolutely right. We obviously can. Likewise, at stage 98, you can say that this is a 2 cluster solution. And stage 97 would mean a 3 cluster solution. 96 would mean a 4 cluster solution, and so on. Okay, till you have a point where you have everyone in individually as a cluster. Okay, so that is like n is to 1 method. Okay, correct. So that's the hierarchical method. So we learned that stage column has to be perceived as the number of cluster solutions, starting from the bottom, where the bottommost means 1 cluster solution, then 2, then 3, then 4, and so on. Okay, so that was about my stage column. Now let's look at the coefficient column. Recall, I taught you in the last lecture that clusters are being formed on the basis of a dissimilarity or a similarity measure. And this coefficient is a dissimilarity measure or a distance measure. So this is actually the squared Euclidean distance which you told SPSS to be worked out using the word linkage. Okay, so this particular distance means the larger the distance, the more dissimilar clusters are getting joined, or the more dissimilar people or cases are becoming a part of your cluster. That is something we do not want, right? So from this, we can understand that this agglomeration coefficient is nothing but a dissimilarity measure. And we are looking for a stopping rule now. So basically the rule which will guide us that, okay, so at which cluster solution do I stop? Do I stop at the 1 cluster solution? Do I stop at the 2 cluster solution, or 3 or 4, and so on? Now for that, please note down the stopping rule. So the stopping rule is when there is a large difference between the coefficients of 2 consecutive stages. This suggests that the clusters being merged or successively joined are increasing in heterogeneity and are too different to form a homogeneous group. Thus, it would be ideal to stop the clustering after that stage. That means you will now find out the change in this distance coefficient. And when you see that, that particular distance is indeed significantly large, then you will stop at that point and you will just look at the number of cluster solutions from the stage column and you're good to go. Now, to do that, I have a sincere suggestion to you all. So basically, it's very helpful to find out the number of clusters in any of the cases. One thing you have understood, that stage column is to be renamed to a column with number of cluster solutions, and this distance coefficient as will be used to find out another variable, which is the percentage change in this distance coefficient. Okay. Now, recall that our data set has 100 cases. And to ensure one of the assumptions in cluster analysis of sample representativeness, we would want that each cluster has at least 10 cases in that. Got it? So you have 100 people and you want that the number of clusters should be such that each cluster has minimum 10 people. So at max, how many clusters can you have? That is 100 divided by 10, obviously. So you can have a 10 cluster solution with, say, 10 members in each cluster. That is the maximum achievable. Okay. Now, this particular idea will allow me to reduce my stages to just 10. So I'm going to pick, okay, so please double click agglomeration schedule. And then what you will do, you will just copy the last 11 stages. That means I'm going to consider the last 11 stages and then I'll take them to Excel and explain you how I'm going to go about it. So you can just copy this. So if you select the cell and go up till 11 stages, this is your one cluster solution. This darkened cell right now. Now I am at 2 cluster solution. This 3, then 4, then 5, then 6, then 7, then 8, then 9, then 10, then 11. Control C, and I have already done it for you here. So these are the numbers. So you can just paste all those 11 numbers here. You can compare. So this is 257. So you see this? Okay. So that's a 257, 274, 294. Correct. So I have a 257, 274, 294, and so on. Okay. Now this is my agglomeration coefficient for the 11 cluster solutions. So I have named a column here, number of clusters. And as I taught you just now, I'm going to rename that column of stages. So you see that? Taking you again there. So this stage column, I am renaming that to number of clusters, such that you're going to start from the bottom and say 1, 2, 3, 4, and so on till 11. Okay. And you also know that I can have at max 10 cluster solutions. Okay. I've written that over here. Maximum number of clusters achievable, keeping in mind sample representativeness, is 100 upon 10 equal to 10. Now, out of these 10 cluster solutions, we are looking for a range of 2 to 4 clusters. Recall, we gave this direction to SPSS and not R. I have been, so I have been working on R as well. So that's why. Okay. Now to do this, I'm going to make a third column called the percentage change in agglomeration coefficient. To do so, I will take the formula equal to, so I can teach you how to put the formula, equal to bracket start, again a bracket, then you give this cell, that is B3, minus B2, then bracket close, then divide. So I have to divide it by original again, that is B2, then bracket close, and then lastly multiply by 100. Okay, then you can drag this to all the cells and you will get it. So I have it over here, so I'm not gonna take those pains. Okay, fine. So this is actually the reason why I took the 11 cluster solutions, because I was looking at this 10 number. Now to find out the change, first cell will always be left out, right? So this is for this reason that I've just taken 11 cluster solutions and found out the change for 10 cluster solutions. Okay. So next is what? We have to follow the stopping rule. What is the stopping rule? The stopping rule was that when there is a large change in the difference, so you look at this difference column, So when you see that there is a significantly large number over here, you have to stop your cluster, your hunt for the number of clusters basically. Now, the question arises, how do I know that it is significantly large? Now to do that, you need a metric. See, always remember, whenever you have to make comparisons to find out, whether this number or this value is significantly higher or less, you need a comparison rod, right? Let's understand that that comparison rod can be taken as the mean of all these percentage change values. So the mean of all these percentage change values can be looked at from here. So that average is coming out to be 12.302. So I've written it over here that mean percentage change is 12.302. So that's 12.30 actually. Okay. Now, since this is the mean percentage change, and you know that you're going to move from up, and when you see that there is a number which is greater than 12.30, you'll say that this can be my optimal cluster solution. Okay, so let's start our hunt. 6.7, nope. 7.2, not at all. Then 11, nope. 12.27, pretty close, but no. 13.38, that is the number which is greater than 12.3. So that means I can indeed stop my hunt over here. So here you check that 13.38 is greater than 12.3. So a 4 cluster solution can be an optimal one. So please note it down that 4 cluster solution might be good for us. But hey, please hold on. Right now, you can't be sure whether a 4 cluster solution would do the good job. Why so? Because when you see that you can have a 4 cluster solution, what you will do is this. Go back to the output. Oh God. Okay, go back to the output and you see here that you have the cluster membership table. Now this cluster membership table tells you that these are the cluster solutions, and in these cluster solutions, how they have put each case in either of the clusters. So basically, let's start interpreting it. For example, about the 4 cluster solutions, because we just found out, right, that a 4 cluster solution might do a good job. Now I need to check something here. Now look at this table, what it tells. So the column 1, which is the case, is nothing but the case number, or the individual number. So this is individual 1, this is individual 2, 3, and so on till 100, because you got 100 individuals. Okay. Now each of these individuals is going to get a label on them. The label being the cluster in which they fall. Okay. So 4 clusters means that this is the 4 cluster solution in which I'm going to give labels from 1, 2, 3, and 4 to each of the individuals depending upon कि वो कौन से cluster में, that is in which cluster do they lie. For example, the person 1 lies in cluster 1, person 2 lies in cluster 1, 3 in 1, likewise 6th person lies in cluster 2, 11th person lies in cluster 4, and so on. So why am I making you really bother about this table is that because I will have to check for sample representativeness. So again, let's copy these, this data and put it into Excel. So for 4 cluster solution, copy this entire cell. Okay, all of these. Control C, go back to Excel, and I've done it for you. So that's my 4 clusters written over here. You copy, the copied portions are pasted here now. Those cluster memberships are pasted right over here. Okay. Now, next what we have to do is that we will check for sample representativeness, because recall, your each cluster must have at least 10% of the data. So 10% here being 10% of 100, that is 10 cases. So I'm going to look whether each of my clusters, that is cluster 1, 2, 3, and 4, has 10 observations in it or not. Now to do that, I'm going to use the COUNTIF function. It's very helpful. So to do that, you just write equal to COUNTIF, okay? And then you give the range from which the COUNTIF has to be applied. So this is my range, okay? Now once you've given the range, you put a comma and you write the equivalent criteria. For example, you're looking forward to count all those observations which are numbered 1. Okay, so that means these are the number of people who lie in cluster 1, and I've written it over here, 49. Okay, now you can go on COUNTIF again, and instead of 1 you write 2, then tab. You will see that in cluster 2 you have 9 people. Similarly, you can put a 3 and then 4, and then you'll easily understand. Okay, oh my god, yeah. And then you can easily understand that in cluster 1 you have 49 people, cluster 2 you've got 9, cluster 3 you've got 14, and cluster 4 you got 28. But here is where your eyes must read. That is, in cluster 2 we have got less than 10 people. Now that is a red alarm, because we needed at least 10 people in each cluster. But again, we're just falling short of one more person, and then this cluster 2 would have done a good job. So it's not that a 4 cluster solution is very bad in our case. It's just that it could have been better. Okay, so if in this particular data set you were by theory guided to pick 4 clusters, then there is no harm in going with this. Okay, but if you had the freedom to go for the second best, then what we will do, because we have gotten less than 10 people here, we will move on to the second best solution. Now the second best solution is the one where again the percentage change is significantly greater than 12.3, and that is a 14.8. That means the 3 cluster solution is our second best cluster solution. Now for 3 cluster solution also, what I'll do, I will pick all these cells. So these are the cluster memberships in 3 cluster solutions. Paste them. So copy them, take them to Excel here. So that's the 3, and paste them here. So these are all the cluster memberships for a 3 cluster solution. Then again perform COUNTIF and see that in cluster 1, how many people, cluster 2, how many people, cluster 3, how many people. And here you see that, your criteria is met. In each cluster, you have at least 10 observations or at least 10 individuals. So that way, I think it's your call as a researcher whether you want to stick with the 4 cluster solution, because it's not that bad. Had it been a 7 or a 6, that would have been a really, really big red alarm. But I think it's perfectly fine if you go with either 4 or 3 cluster solution. And that way we have understood that how, looking at the percentage change in agglomeration coefficient, we stop at a particular point and say that, okay, let's stop here, and this is my optimal number of clusters I'm going to go ahead with. Okay, and then I have 2 suggestions to you. You should be using a 2 cluster solution only when your theory backs it strongly. Your underlying theory is very important in any research analysis. Next, a 1 cluster solution is as redundant as you would have imagined, right? So it is never advisable to use a 1 cluster solution, because obviously that doesn't split my data into anything. So it's good for nothing. Okay, so that was all about today's lecture, and in another lecture I'm going to teach you about the dendrogram. So today the key takeaways from our lecture were that we understood about the agglomeration schedule. From the agglomeration schedule, I intentionally picked the last 11 observations, reason being the sample representativeness. Then I found out the percentage change for the last 10. I picked 11 because I needed to find this change also, which would have come from the 11th observation. Okay. Then after finding this, I compare each value from the mean starting from the top. And I stop at the point where I see that, okay, this number is greater than the mean percentage change, and say that this could be a candidate for my cluster solution. Then I bring the cluster memberships of 4 cluster solution. I paste it over here and check the number of cases. I see that, this might not be very good. So I again opt for the second best. Second best being a 3 cluster solution. See, I'm getting this 403 from here in the number of clusters column, okay, which is the renamed column for stages. So that way I again perform the checks for my 3 cluster solution, and I see that this is okay, this is fine. And lastly, it becomes your call whether to go with a 4 cluster solution or a 3 cluster solution. However, there is one key takeaway more, that is, in a 4 cluster solution, since you're falling short by only one person in cluster 2, so that is cluster number 2, then it might be an indication of a presence of outlier in your data. Now, to check for the outliers, you go back to the agglomeration schedule and see that, so you look at this column. This particular column tells you the stage in which the cluster first appears. And a 0 means that that person or that case has appeared for the first time to become a part of the cluster. Now, if there is a 0 towards the very last stages, whenever you catch a 0 towards the very last stages, say like here, for example, that means those observations have been added very late in the clustering process. So those are observation number 6. There is a 0 here. Observation number 87, a 0 here. Okay. Then 84 also a 0 here. That means these 2-3 observations might act like an outliers in your data. So you might want to get rid of these observations, and then you can rerun cluster analysis and check, what is the optimal number of clusters that you're coming up with, and so on. So that is, I think, for your learning, you can do that later on. So you can just get rid of this 6th one, and whichever was that, I don't remember. That's the 6th, 87th, and 84 basically. Okay, so that's all about today's lecture. Thank you.